Welcome to the 7th video in our quantum computing series. Previously, we covered quantum computing basics and deep dives on quantum gates, quantum interference, and multi-qubit systems. Check out our website, qubit-lab.ch, where you find all the videos, Python code for Google Colab, and more resources. In this new sequence, we start with real-life use cases, applications of quantum computing algorithms. In this video, we will explore the finance use case portfolio optimization using the QAOA algorithm, Quantum Approximate Optimization Algorithm. QAOA is a promising approach in quantum computing for solving complex and highly practical financial problems that classical methods struggle to solve. What can you expect from this video? We will first define and understand the actual problem using a brute force analysis. We introduce QAOA to see how to prepare and execute the algorithm. We examine the results of the QAOA algorithm and compare it with the initial brute force analysis. And finally, we study the optimization of the QUBO function to be minimized in QAOA. We close with some thoughts, outlooks, and final remarks on QAOA in general. Let's start defining and understanding the problem. Portfolio optimization is about defining an efficient portfolio of financial securities in general. Shares, bonds, funds, hedge funds, structured products, or the like. Obviously, we need also to consider constraints when selecting the portfolio. The investment universe for our proof of concept use here shall be 10 shares from the Standard & Poor's 500 index. Each share can be bought at most once. That means each position can be 0 or 1. The available budget for a portfolio shall be $800 US. We have 10 assets which can be selected or not. This leads to 2 to the power of 10 possible portfolios. This is 1,024 portfolios in total. As our efficiency metric, we use the Sharpe ratio. The higher the Sharpe ratio, the more return per risk unit. Risk in portfolio optimization is typically measured by volatility, which in finance refers to the standard deviation of an asset's returns over time. When squared, this measure is known as variance. The annual volatility of a portfolio quantifies how much its returns typically fluctuate, expressed as a percentage over the course of a year. Ideally, in a truly real-life example, we would choose a big universe of assets to select from. Maybe all 500 plus assets represented in the Standard & Poor's 500 index. Unfortunately, we are limited by current quantum computers' hardware. Each asset we want to use here requires 1 qubit in QAOA. If we want to select more than 1 unit per position, this number multiplies. So for our proof of concept approach, we select only 10 shares for our analysis. These are the assets: Apple, Microsoft, Alphabet, Amazon, Nvidia, Meta, JP Morgan, ExxonMobil, Johnson & Johnson, and Visa. For each asset, we download the last year's prices, calculate the returns, volatilities, variances, correlations, and covariances. You find all these downloads and calculations in the Python code for Google Colab on qubit-lab.ch. Now let's look at the 1,024 possible portfolios for our use case. Each dot on this view is one possible portfolio. The x-axis is the expected volatility of the portfolio. The higher the volatility, the riskier is the portfolio, i.e., the portfolio price is more probable to decline or increase. The y-axis is the expected portfolio return. The higher the better in general. Portfolio optimization aims to find efficient portfolios. The Sharpe ratio is a proxy for efficiency. In the plot, the colors represent the possible portfolios, now colored by its Sharpe ratio. The higher the Sharpe ratio of the portfolio, the more efficient it is. The Sharpe ratio is named after his inventor, William F. Sharpe. As you can see, there is an upper boundary of maximum efficiency for each level of volatility. This is known as the efficient frontier, a concept described by Harry Markowitz. Harry Markowitz, Merton Miller, and William F. Sharpe were jointly awarded the 1990 Nobel Memorial Prize in Economic Sciences for their work in the theory of financial economics. When I implemented this exact risk and return visualization some years ago to support client investment decisions at UBS Wealth Management, we used to call the upper left area above the efficient frontier the Madoff zone. In this region, you'd see portfolios with risk-free, exceptionally high returns, an impossibility according to Markowitz's theory. Unfortunately, Bernard Madoff didn't prove Markowitz wrong. He was simply running a Ponzi scheme. So, we are looking for high Sharpe portfolios in or near the efficient frontier. Now we will introduce the QAOA algorithm. QAOA stands for Quantum Approximate Optimization Algorithm. It is a hybrid approach, partly classical, partly quantum, as almost all quantum algorithms. Here you see the quantum circuit of QAOA. There are some hyperparameters tone considered, like the number of qubits, one for each asset in our use case. The number of layers, P. The angles beta and gamma, to be optimized for maximum efficiency of the circuit. QAOA finds the minimum of a quadratic function. That can be used to more academic problems, like the so-called max cut problem, or also for the traveling salesman problem, etc. For portfolio optimization, it is a natural approach, as modern portfolio theory is about minimizing quadratic functions of variances. Let us examine how to prepare our problem for QAOA. There are 5 steps of preparation. First step, very important, is the encoding of the problem into a specific quadratic function, the QAOA. QAOA stands for Quadratic Unconstrained Binary Optimization. The QAOA shall be minimal for the optimal solutions. It is the cost function for the optimization. It assigns to each possible portfolio a single value. The lower the value, the better the solution. The whole idea of QAOA is then to efficiently identify the portfolios with low QAOA values. The QAOA normally consists of several terms. A negative returns term, you want to maximize the returns, therefore negative. A positive risk term, you want to minimize the risk, therefore positive. And any soft constraints, like budget deviation in our case, also to be minimized, therefore positive. Second step, we need to transform the QAOA into the so-called icing format for the quantum approach to work. The QAOA variable x is binary, meaning it can be 0 or 1. In the icing format, the logic is similar, but the variable can be +1 or -1. You can mathematically transform the QAOA into the icing format. The linear part of the QAOA maps to the variable h, and the quadratic part maps to j. No problem. Third step. We must create 2 quantum gates, the cost unitary and the mixer unitary. The cost unitary UC applies a phase shift to the portfolios. Portfolios with low QAOA will be shifted towards a subsequent amplification. Portfolios with high QAOA values will be shifted towards suppression. The cost unitary will be created using the shown recipe. For each linear coefficient h index I, assigning an RZ rotation to qubit I. For each quadratic coefficient j index ij, adding a RZZ gate to qubits I and j. The mixer unitary in the standard form is built as shown. Simply add an Rx gate to each qubit. The mixer unitary UM mixes the quantum states, allowing them to interfere. Constructive interference, amplification, occurs for good solutions. Destructive interference, suppression, for poor ones. The mixer also helps shake up the states to avoid getting stuck in local minima. There are also other mixer variants. If you want to encode the possibility of multiple units per asset position, for instance, you need a custom mixer which does consider your encoding structure. Step 4. sequence, and repetitions. Build a quantum circuit, starting with putting each qubit into a balanced superposition, i.e., adding a Hadamard gate on each. Then you add cost and mixer unitaries alternating in layers. The number of layers p is a hyperparameter of QAOA. The more layers, the potentially better identification of low QAOA solutions. But each layer multiplies the option space for the optimization of gamma and beta. The optimization will get quadratically more complex. In the code, I use p equals 7, i.e. 7 layers. So in a nutshell, we will start the whole process with qubits in balanced superpositions. The process will filter away the high QAOA portfolios and lead to a lowest remaining combination. After many runs of the circuit, you get a probability distribution on low QAOA solutions. Step 5. Gamma and beta tuning. Gamma is the angle you use in the cost unitary and beta in the mixer unitary. You need to tune the variables gamma and beta separately for each layer. This is done in a classical optimization process, a critical key step to ensure the efficiency of the algorithm. With that, we prepared everything for the QAOA to be executed. Now we execute it. First, we must initialize all qubits in a balanced superposition state by adding a Hadamard layer at the beginning. Then we let the qubits pass the alternating UCUM gates as prepared. Then we measure all qubits and get one solution vector. Repeating this will provide a list of hits to be post-processed. Since this process is probabilistic, we must check the results one by one, or at least look at those with a probability above a certain threshold. You might say, if I have to check all the results anyway, why not just do a brute force search? And honestly, if brute force is possible, that's always the best option. But imagine you have 500 assets, and for each one, you can hold anywhere from 0 up to 128 units. That means you need 7 qubits per asset. So 7 times 500 is 3,500 qubits. Each of those qubits can be either 0 or 1, which means you're looking at 2 to the power of 3,500 possible combinations. That's a number with over 1,000 zeros, about 10 to the power of 1,053. That number is unimaginably huge, many, many orders of magnitude bigger than the number of atoms in the universe. There's simply no way to calculate all those possibilities using classical computers. Another idea is to use classical optimizers. With classical optimizers, you can find minimum values in a continuous parameter space. But as soon as you introduce discrete requirements like sector limits or excluding certain asset combinations, it just becomes unsolvable. What QAOA can do, ideally, is to sample maybe 1,000,000 portfolios with low QAOA values from 2 to the power of 3,500 potential portfolios. So you get a condensed list of promising candidates, which you need to check one by one to find the very best solutions. That's really the difference. Quantum approaches like QAOA are more complex, but they scale tremendously better than classical ones. The sky is the limit. We are not done yet. Now you must tune the parameters to improve the selection process and the QAOA encoding of the objectives. This is the critical and time-consuming part of the process. We will have a quick look at how to do this in the tuning section later in this video. But before that, let us look at the results of the QAOA code for our toy problem. As said, you find the Python notebook on the qubit-lab.ch webpage right below the video tile. Here, we see the brute force list of the portfolios on the risk return view. Each dot is a portfolio. The dots which are not colored are portfolios outside of the budget bandwidth. The budget bandwidth has been set to $800 US plus or minus 20%, The colored ones are within the bandwidth and show the value of the Sharpe ratio for it. The more yellow it is, the better is the Sharpe value, and with that, the portfolio efficiency. As you can see, there are two areas of in-budget portfolios to scan. Now we ran the QAOA code on the use case. The result is seen here. Each dot on the right view is a portfolio selected by the algorithm. Again, the colored dots are portfolios within the budget. As you can see, QAOA selected not only portfolios within the budget and not only portfolios with high Sharpe ratio. Why is that so? Firstly, as said before, it is a probabilistic approach. We should get more good solutions versus bad solutions in the selection than in all brute force cases. And it is not so easy to define a single value which reflects all aspects to be optimized at once. The single value to be minimized is the QAOA value for each portfolio. We have to map many dimensions, here maximal return, minimal risk, minimal budget deviation, to just one number. To make this more transparent, we look at this three-dimensional plot here. You see that the QAOA is a complex plane in the 3 dimensions. A properly prepared QAOA approach will select predominantly portfolios which are near the low QAOA area. You can see that nicely in the plot. So there is no clear-cut selection for each criterion, but all criteria mix into the QAOA at once, and the selection will tend towards low QAOA values. As you might understand now, the art of QAOA is the proper design of the QAOA function with the right weighting of the various criteria. We will have a deeper look at it in the subsequent tuning section. Before that, here are the results found in the data. The top QAOA portfolio contains 3 shares: JP Morgan, Nvidia, and Visa. The portfolio has a value of $792, an annual return of 36.8%, and an annual volatility of 24.8%. These are good values. This portfolio has a Sharpe ratio of 1.49. This is third of the top 5 portfolios within the budget band. I reduced the number of shots to just 200, which is below ideal. But considering that there are only 1,000 possible portfolios, we should limit ourselves to see whether we get a meaningful result. And yes, this is a fair result, although we probably needed to further adjust the parameters. Now we get to the tuning part, which is critical for QAOA, as for any heuristic approach. There are 3 criteria in our use case we want to optimize at the same time: portfolio return, portfolio risk, and target budget deviation. Therefore, we incentivize return and penalize risk and budget deviation. These 3 pieces together make up the QAOA value we talked about before. If you look at this plot, you can see how each of the 3 components contributes to the total QAOA value, which is shown as black dots forming a swoosh. The lower the value, the better the solution. The blue dots show the return incentive. The bigger the portfolio, the lower its negative contribution to the QAOA, which basically means the returns improve in bigger portfolios. The amber dots represent the risk penalty, and here you see the opposite. When the portfolio gets bigger, the risk penalty in the QAOA goes up, so the risk is seen as worse. If you think about this for a moment, you might wonder why. Normally, you would expect that a bigger portfolio means lower risk and probably lower return too, simply because you have more diversification. But in our QAOA, we translate both return and risk to an US dollar amount. So the absolute dollar amount you are putting at risk actually increases as you invest more, even if the average risk per asset gets lower. The same idea applies for return, but in the other direction. Now, The budget penalty, that's the green line you see in the background, is a thin curve that goes up quadratically the further you get from the target budget. This basically punishes portfolios that miss the target investment amount. The further away, the bigger the penalty. For the total, you can look at the black dots. They show the sum of all these penalty and incentive terms. Again, lower is better. Now you can probably already guess we can and should change the weights of these three components to improve the selection process. If you make the budget penalty way too large, risk and return just don't matter anymore. And the algorithm might even only select the zero portfolio, because that is where all the multipliers go to zero, and that can be better than any non-zero solution. So this whole thing needs a careful touch. And it's important not to forget that we're not just looking at three separate lines on a plane, but at a multi-dimensional dot structure in space. Alright, let's put this into practice. The picture here shows the situation for a budget penalty factor, alpha, of 10. Going a step further, you can now also change lambda and examine the impact. Here is an overview for alpha equals 0, 1 and 10 horizontally, and lambda equals 8 and 15 vertically. For our code and results, we used alpha equals 10 and lambda equals 8. This is the right tile in the upper line. A higher alpha will enforce the budget constraint better. On the other hand, changing alpha from 10 to 2, as you see the plot to the left, reduces the QAOA values overall. And you'll notice the risk swoosh and the return swoosh both get broader, as the QAOA algorithm normalizes the values when choosing proper rotation angles. That means the budget part becomes less dominant, while risk and return increase their influence. When the swoosh is broader, you have more differentiation for risk or return within the same budget. But when it's narrow, there's less difference. Budget takes over. If we set alpha to 0, then the budget penalty disappears. For the lower line with increased lambda, the risk gets more relative weight. Take a closer look and examine the impacts. Here's a quick overview of how the budget constraint affects the invested assets. On the left side, you see the distribution of the portfolios for our budget of $800 US. The selection is not very tight, but the center of the portfolio's invested assets is around the target budget. On the right side, for comparison, the values if we change the budget to $1,700 US. So the mechanism seems to work, although I must admit, I used an additional little trick, adding an extra piecewise budget penalty to the energy evaluation in the QAOA expectation function to further enhance constraint adherence. You will find it in the code on qubit-lab.ch. So far, we only examined the QAOA value versus the invested assets. But even more important is the Sharpe value as combo for risk and return. The plot to the right shows the QAOA value for each portfolio's Sharpe ratio, separated by our three terms budget, risk, return, and the black total. We see that on the left side, the lowest total QAOA values, the black dots, are found for invested assets around the budget. On the right side, we see that the lowest QAOA values are at the highest Sharpe ratios. This looks fine. As we are minimizing the QAOA value, we might expect the QAOA algorithm to select portfolios towards higher Sharpe ratio and invested assets around the defined budget. There is, for sure, much more potential to enhance the QAOA parameters and also the QAOA hyperparameters. Finding those is a time-consuming process. There are many possibilities to change the weights or to select the units of the components. Risk can be a pure variance or in squared dollars or squared dollars by squared budget, etc., etc. This is where the experts can really shine. Before we finish, I want to touch on a few important points and give you some thoughts for the road ahead. First, when it comes to constraints, there are many ways you can handle them in quantum optimization, not just what we discussed here. You can implement soft constraints, apply hard constraints, do some pre-selection, or even rely on post-processing. Each approach has different implications for your results and your algorithm's complexity. Next, let's remember that tuning plays a major role at two levels. On the one hand, there's tuning the QAOA formulation itself, choosing things like lambda, alpha, and deciding how you normalize each term. On the other, there's tuning the QAOA algorithm, such as setting the number of layers, optimizing gamma and beta, and designing the mixer. Both are crucial if you want meaningful and efficient solutions. If you're working with multiple securities per position, things get more complex quickly. You'll need multiple qubits to represent each asset's quantity. And that, in turn, means designing a custom mixer to handle the encoding properly. Another big difference in this field is between stochastic and deterministic optimization. The QAOA approach works with probabilities, so you need to sample, tune, and use post-selection to pick out good solutions. That stands in contrast to classical optimizers, which tend to be fully deterministic. Finally, let's be honest about where we stand with quantum hardware. Current quantum computers only support a few dozen usable qubits, and they're still very noisy, which makes large-scale applications infeasible. And while simulating quantum circuits on a classical computer is possible for small problems, it quickly becomes impossible as the number of qubits grows beyond more than about 20 qubits. So, these are some of the challenges and possibilities ahead. There's still a lot of ground to cover, and a lot of open questions, but that's also what makes quantum optimization such an exciting space to explore. Alright, that's it for this session. Our very first video diving into real-life applications of quantum computing in finance. Thanks for sticking with me to the end. I know this isn't the easiest material, so you can honestly be proud of what you've accomplished. I'd love to hear your thoughts or questions. Just leave a comment or send feedback. And don't forget to check out qubit-lab.ch, that's qubit-lab.ch, where you'll find all the videos in this series, plus Colab notebooks, Python code, and a bunch of extra resources to help you get hands-on. As for what's next, I'm still deciding, maybe a deep dive into risk management, or we might look at Monte Carlo simulations with quantum algorithms. If you have a preference, let me know. Thanks again for watching. Hope you're starting to feel that unique quantum vibe, and I really hope to see you again in the next video. Until then, have a great day.